Hey guys, welcome back. We're talking dynamics, we're talking impulse and momentum, and here we have what I'm calling a composite example. So we have a rocket sled that you are in, and it is riding along a frictionless track, and it's propelled by this thrust that we have in this diagram here. And we are given that it is a 4 megagram sled. That's 4,000 kilograms. Friction is negligible. And we're asked to find first the max V and then the displacement at t equals 35. So let's get to it. I like this example problem because it gives us an opportunity to use what I'm calling a composite method. So we've seen this two-stage acceleration before, and we could do this equation twice, right? We could do it for the first section, and we could do it for the second section. I think that's how they do it in the answer key, but we actually don't have to. So if we start with the impulse equation, then we have mv1 plus the impulse, so f dt equals mv2, right? And we're given that we're starting from 0, right? So this is 0, and we can split this, right? And consider both of these simultaneously. So if we do that, then what do we have? We have the force in the first part. So we're going to have two integrals. We're going to add them together. And so we're going from 0 to 25 here. So 0 to 25 seconds there. And let me do this. Instead of just saying that, I'll say t equals 25. And what is the thrust? The thrust is 4, and this is in kilonewtons, so 4,000. 4,000 t to the 1/2. That's dt. And then we're going to have our second integral here. And this is going to go from, here we're going from 25 to, we'll say t equals 35. And what is this? This is the starting point. So 20, we have 20,000 over 35 minus 10, that's 10 seconds. So 2,000 is how far we're dropping, and this is 35 minus t, right? Okay, and that is dt, and that's going to be equal to mv2, and this is a frictionless system. The thrust is causing it to accelerate the entire time. So our v2 at t equals 35 is going to be our max v, right? So the mass is 4,000. So 4,000 kilograms times v max. Okay, well, that's handy. We can reduce this. So these drop out. This becomes 1/2. And if we rewrite this, we can solve this one, right? So this is, what, 1/2. Wait, I should just teach myself to do the variable first. So this is going to go up to 3/2. So that means that this will be 2/3. And we'll be evaluating this at t equals 25. So from 0 to 25 plus, and let's see, this is 1/2 t, so this is 17.5. And we put a bracket around here so we don't get things confused. So 17.5 t minus 1/2 t, and this is going to be t squared. So 1/2 times 1/2 is 1/4 t squared. We're going to evaluate this at 25 and then at t equals 35. We could just do 35, but we need to make this distinction for the second half of the problem. And that, again, that's going to be equal to Vmax. Okay, so here, when I run this through the calculator, here I get 83.33 plus, and there's no zero, right? Plus, and I'm gonna keep the t, and what I need to do is to turn this into an equation that I need in the second part, and then I'll solve it. So an intermediate step. So 17.5 t minus 1/4 t squared. And then this is going to be minus 17.5 times 25 is 437.5 minus 156.25. Again, that equals Vmax. Okay, so what do I need to do? I need to combine these and this. Right, so what is this? 437.5. This is minus 281.25 plus 83.33. And we can write this now. So this is equation going to be, this is going to be minus 1/4. Right. Well, I can do better than that. Minus 1/4 t squared. That's 17.5 t. And this is going to end up being minus 197.92 equals Vmax. Okay, and when I come back up, use 35 for t, then we get that Vmax is equal to 108.33 meters per second. Okay, in the second part of the problem, same strategy. And now we're interested in S when t equals 35. So again, back to this idea that we should use the variables that we have to see if we can figure out which equation to use. Well, we have t, s, and v. And what that tells me is that the equation that we should use, so for part B, we'll start with v equals ds dt, right? S, t, and we have v. So then when we separate this, then we get s, which we're after, is equal to the integral of v dt. And again, we can just split it and add this up. So what do we get? We get s equals, our first integral is going to be from 0 to 25, right? So this part of the curve right? And so we're going to integrate this guy. So 2/3 t to the 3/2 dt plus this integral here. And this is going to be from 25 to t equals 35. And that is minus 1/4 t squared plus 17.5 t 97.92, and integrating this is S. It's actually not as bad as it looks. So S, and what we have 2/3. That's going to be multiplied. This is going to become 5/2, so times 2/5. And then this is going to be times t to the 5/2, but we're only going to be interested in 25, so, and then this will be to the 5/2. And when we run this through the calculator, we get, this is 833.33. It's going to be plus, here, let's see, this is minus 1/4. It's going to be t to the 3, so it's minus 1/12. T to the 3rd plus 17.5 over 2 is 8.75 t squared, and then minus 197.92 t. Now we're going to evaluate this from 25 to 35. Okay, and when you run these through, hopefully you have a good calculator that can do these quickly. Some calculators can do this in one set. And when you do that, then you get that S is equal to 1,833 meters, or 1.833 kilometers. So again, the point here is that when you have a composite force profile, often you can just put it together and use your impulse one time and save about half the work. So at any rate, I hope you enjoyed the video, and I will see you in the next one.